Fine. So it's my pleasure to introduce Chunli Huang, with whom I have a close relationship, I would say. He was co-advised by me when I was in Taiwan. The other co-advisor was in Singapore, Elon Chong. And after graduation, well, he started working on graphene together with me, mostly on spintronics. But after graduation, he moved to the United States and to Austin. And he was working with Alan McDonald. He's going to present some work that he did while he was a postdoc there. And well, I mean, apart from what he's going to talk to today about, which is superconductivity in twisted bilayer graphene, and I would like to say that the fact that we had two talks on twisted bilayer graphene, I mean, two consecutive talks on twisted bilayer graphene, is just a coincidence. I mean, we will change subject in the next one. So, but he started working on twisted bilayer graphene in Texas with Alan, and he has been touching on a variety of topics there, not only superconductivity, which is what he's going to be talking about today, but also on magnetism and many other subjects. But today is superconductivity, so we are all looking forward to his talk. So without further ado, I just let him talk. Okay, so thanks, Chunli, for waking up so early.
Okay. Thank you for the introduction, Miguel. So I'll just go straight in. So today I'm going to talk about a picture of superconductivity that we have been puzzling for a very long time here in Texas. This is a work done in collaboration with Namin, Wei-Ching, and Alan McDonald. And they acknowledge very useful discussions with Yongjun, Elisa, and Andrea. So just to get everyone excited, I'm going to remind you guys, what is really the magic of Moray superlattice. So what you see here, can you guys see my cursor?
Yes, it's visible.
Okay, good. So what you see here is a twisted bilayer graphene. As you can see, there are two layers of graphene twisted at a small angle. So once you twisted this, you form a superlattice. And the area of the superlattice is enhanced by a factor of 1,000 roughly, a very small twist angle. Okay. So the magic really happens when you start to putting electrons one by one, or holes one by one, into this Moray unit cell. Okay. And the way we measure the amount of electrons or holes in the Moray unit cell is to borrow the terminology from quantum Hall effect, called this a filling factor nu. Okay. And so nu is nothing but the product of electron density with the Moray unit cell area. So it's a dimensionless number. So let us see what happens. So if you start at nu equal to 0, this is a neutral graphene, right? So you have a bit of resistive peak, as you can see here, but it's common to all graphene, right? If you go to Dirac point, you always have a resistive peak. So the magic really happens if you're adding one electron into this 1,000 of atom unit cell, and suddenly the system pick up a huge RXY, okay? And RXX dips. So we call this a correlated churn insulator, but it's really just a anomalous Hall insulator with almost, if you calculate the Hall angle, this is almost pi over 2, right? And if you add in another electron, the things change completely. The Hall resistance is gone, and the resistance, a longitudinal resistance, shoot up. And this is a correlated insulator. You add in one more electron, this thing becomes a correlated insulator with a bit of twist, a small temperature. And finally, if you fill up the Moray bands, I drop a jargon here, Moray bands, but I will explain what they are later. So if you fill up the Moray bands, then you get a band insulator. So let me just remind you guys that according to band theory, at filling factor 1 to 3, you should just get a metal. So the fact you see all these interesting correlated insulator, sometimes with anomalous Hall effect, is really telling you a correlation effect. Coulomb interaction is playing a very important role. And this is really the attractive part about these type of systems, that it allows you to play around with all these insulators and anomalous Hall effect. Arguably, the most exciting feature of this phase diagram is probably this guy. Okay, this is a superconductivity dome, and it occurs typically beside nuclear to -2 correlated insulator. Sometimes it also occurs in the electron side. It's weaker in the electron side. We don't know why. And this type of phase diagram, it's very routinely seen by many other experimental groups. So I took this data from Dmitry Yefitov's group because it shows superconductivity and correlated chain insulator in the same sample. But there are also other data. For example, the most famous one is the first discovery by the MIT group, Santa Barbara, so and so on. The list goes on. Okay, so my aim today is really to give you a picture of what we think is happening. Okay, so this is the main message. We think the superconductivity, there's a particular channel that when it becomes attractive, it leads to superconductivity. Okay, and it occurs between -2 and -3. This is Coulomb-based non-phonon. This superconductivity dome is a valley singlet spin triplet, and it is suppressed by a tendency towards valley polarization. Okay, so my job today is to convince you, since this picture is consistent with most experiment, it cannot be too terribly wrong. Okay. Right, and the way I aim to do that is to first, just go through briefly about the basic theory of twisted bilayer graphene. Since Hector 2 weeks ago have already mentioned a little bit, I'll be brief here, and then I will talk about my interpretation of the complicated experimental landscape, and lastly, I will then present our theory. So. By the way, if there are any questions, I think people can just unmute themselves and shout. That would be easier. So, right. So let's go through the basic theory first. What you see on this slide should be very familiar. This is the band structure of graphene. And you see all states are gapped at the zone boundary by the honeycomb lattice, except at 2 points that we call valley, K and K prime. At these 2 points, the conduction band and valence band come together and touch, and it's twofold degenerate. Okay, if you open a gap here, you create a winding of. So what you see arrow here are the relative phase of the wave functions between the A and B sublattice. So if you open a gap here, it creates this winding number, and this I think by now is really a textbook example of topological band theory. Okay, so what is not a textbook example is how to think about Coulomb interaction and band energy in terms of this band touching systems, right? Where Fermi energy sits right there in the undoped case. So I'm going to promote a way to think about Coulomb interaction versus band energy by visualizing the polarizability of an octet pseudospin that contains a sublattice degree of freedom, or if you want the band degrees of freedom, they are the same. Valley degrees of freedom because we have 2 valley, low energy, and spin degree of freedom because you have 2 spin degeneracies, right? So as you see later in the talk, this will turn out to be a very useful concept to understand interactions. Okay, so now let us introduce, take 2 layers of graphene, twist them. Right? So you have seen this image earlier, and now don't stare at it for too long, you get dizzy. But I draw 2 red arrows here for you. It's supposed to be the lattice vector of the Moiré unit cell. Okay, and you can see this is Moiré potential. So what Rafi and Allen set up to do is to find a set of block orbitals that solves this unitary eigenvalue equation. I mean, this block condition, and where this is really a 4-component vector at each k. Right? You have A1 in layer A and B in layer 1, A and B in layer 2. So they really just set up to find how do we find the dispersion of these block states. And what they found is if you twist them at a certain angle, the spectrum of these block states are concentrated around 0 energy. You can see here this is, and at that time they don't know why this happens. They call it the magic angles. And but they predicted if you have strong interaction effects, you're going to have a lot of interesting physics. So that's the prediction. A few years later, now we understood why this happens. Oh, by the way, this is what people call the flat bands, because you see they're really flat. But fundamentally, it's really because the spectrum wants to concentrate at the 0 energy. So of course, 0 energy is very special, as we learned from quantum Hall effect. And a few years, I think, 2 years later, 2 years ago, the Tanapolsky from Harvard did a very beautiful work to explain what is the origin of magic angle in twisted bilayer graphene. So you say that if you fine-tune the Moiré potential, okay, so that the block Hamiltonian has this property, sigma z is sublattice. So what this means is when you change sublattice from A to B, you flip the energy, okay? And they call this the chiral limit. So if you're in this, if you tune the VM to this chiral limit, then they can show mathematically that the number of 0 energy states is actually equal to 2 times the number of K points. That means you have 2 completely degenerate flat bands at the 0 energy. But this requires a bit of fine-tuning. Okay, so this is Moiré potential. Now let me add in Hartree energy. So as I mentioned earlier, the Moiré potential, the exact flattening of the bands requires fine-tuning. So it's not too surprising that if you add in a self-consistent Hartree energy at each filling factor, is going to modify the Moiré potential and enhances the dispersion of flat band. And this is indeed predicted and shown in this paper, where you can see, just to give you a flavor, this is the what I call Moiré band, because this is a band structure created by Moiré bands. And this is for nu equal to 0 at neutrality. You see at a gamma point, both bands are lowered in energy than the kappa points. However, we go to nu equal to -1, this changes completely. The energy at gamma point is actually higher than the energy at kappa point. That just gave you a flavor that the band structure really changes when you change your filling factors. And this is really because of the competition between the Moiré potential and the Hartree self-consistently generated Hartree potential. And this has received some experimental support. What you see here is the data from Caltech group. So this is STM data, magnetic field enhanced local density of states at large twist angle to avoid superconductivity and other magnetic states. It's a bit hard to, it takes some time to really fully understand that data. I invite you to indulge yourself in this experimental work. It's very nicely written, and you'll see why I say such data really supports this band renormalization picture emphasized by Paco and co-workers. So I've mentioned about the periodic potential, the Hartree self-energy, and the last thing I have to talk about is fog, right? So so in terms of fog self-energy, we know in quantum Hall effect, okay, when you don't have any kinetic energy, exchange energy leads to fully spin polarized ground state. So that means you try to write down many-body wave functions, right, n-particle wave functions. You have x1, s1, the orbital and spin content of first electron, second electron, n electron. You can really separate them into just the orbital part and the spin part. Okay, and I'm going to claim, and this is almost I don't have to claim, this is known to be lowest Landau level exact wave function, right? Why? Because the spin is maximally symmetric. So the wave function part is maximally anti-symmetric. So you change any of the two, you get a minus sign. And because of this property, it minimizes the Coulomb interaction. And there's no way the correlation energy can no further lower the energy of this state. And hence, this is the lowest, this is the exact wave function projecting the lowest Landau level. Now we expect something similar to happen in measure angle twisted bilayer graphene, because it's kind of similar, right? Because the band energy is very small, right? It's not zero, but it's not dispersive, and the exchange energy is much bigger. So indeed, the mean field yields a fully pseudo-spin polarized ground state. By that I mean it is the many-body ground state is really a slated determinant of this kind of block states, where you only feel one out of the 8 octet pseudospins. Okay, right. So by that I mean, if you look at valley K, you have 4 bands, right? Conduction valley up down. Okay. Valley K prime same. So in total you have 8 bands, and the state always occupy one of the bands completely. At nu equals to -3. If you ask them to fill 1 electron, you will always do this because then the orbital part will be maximally antisymmetric, and this lowers the Coulomb energy. It's hard to show that this is anything. I think this is quite close to the exact wave function in the sense you can only change. You cannot change the distribution of occupation numbers. You know, you always occupy this, but you can probably change the wave function content of the band. That's what correlation effect would do. But nevertheless, this has an immediate experimental consequence. Okay, and it's a remarkable one because these bands also happen to be Chern bands. They have Chern number, and you completely occupy them. So when you sum over the Chern barrier curvature and all the distribution, all the occupation number is 1, you just sum over all the barrier curvature, and it gives you a quantized Hall resistance. And this is indeed seen in the experiment. This is the data by Andrea Young group, but similar data, not so quantized, has been obtained by the Stanford group. Right. So that's everything that we need to know about basic theory. I've talked about Murray, Hartree, and Fogg. I will now talk about experimental landscape. But are there any questions for the first section?
Yeah, feel free to
I have one.
Hi, Ilya.
Yeah.
Yes.
Yeah. Well, actually, I have it even at the very beginning. You say there is a Chern number or Chern insulator. This requires a broken time reversal, as I understand. How it happens here is because you have spin polarization and the time reversal symmetry is broken.
Yeah. So Ilya is very, very sharp. He realized I have this. I planted a question, right? Because I say it's due to orbital moment condensation. just to remind everyone, quantum anomalous Hall effect before twisted bilayer graphene is typically seen in material that has huge spin-orbit coupling, and you try to magnetize it, right? So it has to do with spin polarization and spin-orbit coupling, right? But here in graphene, spin-orbit coupling is weak. It's carbon atom. It's very weak. So the way you break time reversal symmetry is really due to the fact that the system selects occupied. So each of these bands has a given orbital moment because they live in a given valley K. So maybe this will help. So let's say if you go to a valley K, you open a gap, then you have a winding of you have a winding, okay, and this carries orbital moment. So if the two valleys have the same winding, then they lead to anomalous Hall, the Haldane quantum anomalous Hall effect. If they have opposite winding, meaning that they don't break time reversal symmetry, then they have the Valley Hall effect. So you break time reversal symmetry in this system by condensing in only one of the valleys, because in the other valley the occupation number is 0, and this valley all the electrons have certain orbital moment. Does that make sense?
Yeah, probably. And how do you choose? So it's spontaneously.
Yes, exactly. This is spontaneously chosen, and if you go to this paper, they will show you how you can flip this. So sometimes there are domain wall, and then you have to clean the domain walls with magnetic field, with current, but it is spontaneously chosen. At least we don't know any small energy scale that shows this. Yeah.
So can I follow up?
Yeah, sure.
This sector. So the thing is that in order to certain number, in addition to valley polarization, you need some staggered. You need to break a Sublighted symmetry somehow, right? So this is so when you talk about in this slide about pseudo spin polarized ground state, but there is an implication that there is some staggered polarization, no? Some inequality.
Yes. So yeah, I follow you. So you see here at kappa and kappa prime. Well, okay, this is probably not broken, but you can see here this is clearly broken just by the ground state. Now in the experiment, Hector pointed out it's important to break the sublattice polarization to open a gap at kappa and kappa prime. These are really the kappa and kappa prime are really the descendants of the Dirac point from the original untwisted graphene. Okay, so in this experiment, they actually enhance this breaking of kappa and kappa prime by aligning a boron nitride. Okay. But that's not really necessary, because you can see in this sample, the data by Yefitov's group, they don't have to align boron nitride, and just twisted bilayer graphene alone, they can see a quantum anomalous Hall effect, but at nu equals to 1. Yeah.
Yeah. So in Yefitov's data is spontaneous, no? This sublattice.
We think it is spontaneous. There's no sign of align. At least, there's no intention to align boron nitride. So yeah, I'm not sure about the distance. I think it's a bit far. So I think it's fine. Yeah, I think you can call it spontaneous. Yeah. Okay. That's great. Should I move on?
Yes, please.
Yes. Yeah. Thank you.
Okay.
Thank you.
Welcome. Yeah. That's great. Right. Now, since this is a recorded talk, and now I'm going to talk about my interpretation of experiment. So I'll be brief. But I heard there's a coffee break. I can speak more freely in the coffee break. Okay. Right. So I'm going to show you a few guidelines about how we formulate a theory. Okay. So guideline number one, this is the data from Andrea's group. What you see here, is our favorite classical Hall effect. Just remind everyone, in the weak field limit, where you linearize Rxy to linear B, is independent of transport lifetime. So what it measures, it only depends on NH, and NH is called a Hall density. And now let me measure NH the same way I measure the electrons, the carriers that you introduce in the electrons, using this filling factor. So now let's do the experiment. Start from charge neutrality. Okay, start from here, and you remove electrons. Okay, so introduce holes. So what happens is that you see the Hall density goes up, goes down, all the way down with a linear slope up until -2, and then suddenly jumps. Okay, so so when the Hall density has a given sign, it means whether you're electron or hole. So in this case, this is a hole-like Fermi surface. Okay, and it shows that if you remove electrons into the system, you have a hole-like Fermi surface, and it grows and grows and grows and grows until -2. And suddenly at -2, the system decides, bang, it comes back down. Okay, and we call this a reset transition. So such a reset transition means your Fermi surface reconstructs and becomes very small, right? But it doesn't change sign, so it's still a hole-like Fermi surface. Now, this must show up in the resistance. There's no way you can avoid this. So you see here, you come to -2, the system suddenly becomes very resistive. Okay. Now, as you further remove electrons, you keep coming down again, and until -3, you go through a reset again, but this time it's not as strong as -2. The Fermi surface after a reset is still, is still finite, not as small as this. So you see the resistance drop is not so, strong. The resistance enhancement, sorry. And after this, the system then hole-like Fermi surface increase again, and then it hits a Van Hoff singularity. So by that I mean, when you come to this point, the Hall resistance changes sign through 0. So you go from hole-like Fermi surface to electron-like Fermi surface. Because the hole then the Rxy has to change sign through 0, the NH or new H has to go from -infinity and come back from +infinity, right? And so this is sort of a sadder point, if you wish. And then if you keep removing electrons, the Fermi surface is gone, and then suddenly, I don't know, maybe some cosmic ray come in, and then there's a dip here, and then that's it, right? That's the entire evolution of the band structure seen by the Hall density. And the important point is the superconductivity occurs here between -2 and -3, as you can see here, the dome. The Van Hoff singularity is here. It's outside the dome. It's sample dependent. Some samples shows that the Van Hoff singularity can come close to -3, but it's never right in the middle of the dome. Okay, that's all I have to say for guideline number 1. Oh, I'm doing very bad on time. Okay, so number 2, you have spin rotation symmetry. The normal state breaks spin rotation symmetry. So this is a TC dome. You increase the in-plane magnetic field up to 10 Tesla, there's still a TC dome surviving. Okay, so so you can this is the experimental data from the MIT group. You can see that let's say at filling factor 2.28, where the dome peak. Okay, the magnetic field that requires to kill the superconductivity, it's very large. How large? At least 2 to 3 times larger than this line. Okay, so this line are the Zeeman field. The Zeeman field needed to break the Cooper pair, the singlet Cooper pair. So this means the normal state must have its spin rotation symmetry broken. Okay. Number 3, the insulators and superconductors are independent. So this is Andreas data. This is Caltech data. So you see at about filling factor -2, in this sample, you are close to measure angle. Measure angle is 0.5, and the boron nitride is very far away. Okay. So in this case, at nu equal to -2, you have a strong insulator, right? The resistance goes down as you go up in temperature, so it's strong insulating. And you have a superconductor next to it. In this sample, you twist your system away from measure angle, the bands become less flat, and you make the boron nitride closer, so they are more screening. So Coulomb interactions become weaker, and the resistance, the insulator is gone. You don't see it anymore. Okay. Yet there's still a dome, superconductivity dome. Similarly, in this device, for example, you don't see any insulator in the phase diagram, yet there's still a superconductivity dome. Okay, so this shows insulator and superconductors are not, they are independent.
Sorry, Chunli, can you explain again what is the difference between the two samples here? I mean, the first one, you bring it closer to, to the BN, right? And the second one, the lower one is what?
Let's just talk about A and D on the on this data by the Caltech, Santa Barbara group. So this is closer to, there are two things you can change. You can change the twist angle, or you can change the boron nitride distance.
Yes.
So the twist angle, the closer to 1.05, the stronger, the flatter the band. So strong insulator. And the distance of boron nitride, I think the thicker, the closer you are, so they have a graphite gate to measure this. So the graphite gate can screen the Coulomb interaction. I think it is graphite gate, if not metal gate, but in any case, the gate will screen the Coulomb interactions. So you can control that by boron nitride thickness. But it's also a bit tricky because you change the thickness, there might be disorder issue, but these are things that experimentalists have to worry about. Yeah. Okay.
Yeah. So the lowers. I mean, the other group is what do they do?
The other group is a bit
different twist angle, right? But so
the other group is I didn't have time to go into the details, but the other group is slightly different. They decided to do they have you can see a metal gate, and then they have actually a tungsten diselenide. Okay, so this tungsten diselenide, I forgot the dielectric constant. I'm not sure anyone in the call can recall, but it has a large dielectric constant, and they used tungsten diselenide to twist to screen the Coulomb interactions.
Oh, okay.
And these are done at different twist angles. Yeah. I should say there's also one data from Dmitry Yefitov's group that sees something similar. Yeah, but I don't have time to talk about that. Right, I'm very lag behind, so let me rush a bit. So these are the summary of experimental guidelines. 4 points. Normal state has Fermi surfaces, but we don't really know the Fermiology, especially after the reset transition. Number 2, normal state has broken spin symmetry. TC has a dome, but insulators and superconductors are independent. And number 4 is just empirical evidence. Right now, we don't see any evidence of superconductivity when your bilayer graphene is aligned with boron nitride. So, okay, so with all those basic theory and experimental landscape, now let me talk about pseudospin paramagnon. Right, let me just, let us go back to 1966, okay, to understand all the experiments that I just show you. So in 1966, there are two burning questions. There's one asked by Buck and Triplet. They ask, why is the superconducting TC suppressed towards the end of transition matter series? So this is the first chapter in the volume 2 of POX. You can see this is the TC, and this axis, if you go in the x direction, is towards the end of transition series, palladium. Okay, and you can see the TC drops. So they want to know why. The answer is on the right-hand side, but they cover it. And the other question is asked by Donia and Angersberg. What is the origin of excess entropy at helium-3 when the temperature is much smaller than the Fermi temperature, like 2 orders of magnitude smaller, about that range. Okay, so and this is this data. So this is like 30, 40 millikelvin, much smaller than the Fermi temperature. So the linear in T heat capacitance, which would normally measure the density of states, should have some correction at T divided by T Fermi square, and that should be nothing. And yet they see this trend. Okay, and this is at low pressure. At high pressure, this is much more significant. So the common answer to these two questions is this concept of paramagnon, and I took this figure out from Phil Anderson's book. Okay, so what you see on the y-axis is the spectral weight for spin fluctuation, and the x-axis is basically the frequency of the fluctuation. So now you see the imaginary part of this quantity. According to Fermi liquid theory, we can all remind ourselves it's just proportional to omega. Right? And the slope is then a 1 over q. Now, this changes dramatically if the system approach a phase transition. Let's say, you try to push palladium into a ferromagnet, or helium trying to go into a solid. Then at those phase boundaries, in the paramagnetic phase, at the phase boundaries, there's enhanced spectral weight at low frequency. So this piling up of spectral weight at low energy is known as the paramagnon peak. So it's just like a magnon peak, but it's in the paramagnetic phase. And this induced paramagnon peak, as you can imagine, dramatically modifies low energy properties of Fermi liquid. Okay, and this is the answer to these questions, to these two questions. So Buck and Triplet say, okay, if I want to understand why the TCs dropped towards the end of transition matter series, I basically have to sum up what is now known as a Buck-Triplet diagram, where you see you have a particle hole coming in here, you have a particle coming in, and then you scatter into a particle. You create a particle hole, okay? And the hole and the particle repeated scatter, and eventually it combines with another particle that comes in. So if you take into account a series of this diagram, then you will find that the paramagnon induce a large singlet state repulsion. And this is shown here. The drop of TC is associated with enhance of spin susceptibility. And this is really an enhancement, not just because the density of states become bigger, because you can take chi divided by gamma. Gamma is a linear in T heat capacity. I think this is called a Wilson ratio. Yes, it's called a Wilson ratio, and you can see that it goes up. Okay. Now, and you can take the same type of diagrams, okay, and put it in the self energy. Okay. And now, you can calculate then the entropy by taking the derivative of the energy with respect to temperature, and you can get, and then you'll be able to explain this type of behavior, that is really not T square over TF, T over TF square that matters, is T over TF square log T, and the log dependence dramatically modifies this is basically a log dependence that you're seeing, okay? If you go to the paper. Okay, so this is 66. Nature is still hiding the secret below 2 millikelvin. We have to wait for 6 more years before these three gentlemen reveal the wonderful superfluidity phase, the superfluid phase in helium. So the main message to theories, as I see from this discovery, is that first principle calculation of pairing interaction is very difficult. Okay, so we have the recipe to calculate TC. Right? You just have to solve this type of equation. This is a pair susceptibility, and this is a pairing interaction. But we don't have the recipe to calculate gamma. Right? We know gamma by symmetry has to have a spin symmetric channel, spin anti-symmetric channel. But people have tried very hard to calculate this thing to the best of their ability in the 60s, and predicted, most of them predicts D wave. But the experimental data clearly shows a P waves from the NMR line shift. So, right. So nevertheless, Phil Anderson, in less than a year, this is 72, July, in less than a year, he explained triplet superfluidity in helium-3. So how does he do that? So he basically combined the two paramagnon ideas in 66. He say, you know, there are evidence of paramagnons in helium, and I know that paramagnons suppress singlet pairing, but it actually enhances triplet pairing, and that's how he explains superfluidity. So let me just go through, use you know, free section to go through Anderson's algebra, because that will be important in my later talk. Right. So let's say you start with right. So pair interaction for the triplets. You just have to consider up, and then symmetric plus anti-symmetric channel. Now the symmetric channel is just a rho. Is the density fluctuation. So this is sum of bubbles, and this is a sum of ladders. This is ZZ. Z is the spin fluctuation. So, and the pair interaction for the triplets is just a difference between these two geometric series. But I just told you that, you know, it's not good to calculate this to the best of your ability. You should calculate this to illustrate your pairing mechanism and use some experiment to you know, exclude and falsify. And this is what Anderson did. Okay, so you try to estimate the average pairing interaction strength by summing up the paramagnons. So as you can see in this equation, this is just this guy. Okay, you can recognize a few factors here. You know, Q squared divided by 12kf squared is the linear function, and you sum over this thing in 2D. I know in 3D it gives you a log. This is only the log at Q greater 0. And the rest that you don't know, you can just lump into this repulsive interaction. And repulsive interaction is AS. He didn't even try to estimate AS because we know already AS will be very badly predicted. It's very badly captured by paramagnon model. So, and then he did a Anderson style estimates. He said, I know the spin susceptibility is enhanced by a factor of 20, close to the melting curve, right? So 3/2 over log 20 gives you 4.5. And then he can invert the Macmillan formula. He knows what's the experimental TC. He knows what's the Fermi energy, so he can know this. You know the right answer. Now the distance between the right answer and the and his glue must be then the repulsive interaction. So this is how he estimated the repulsive interaction. And then he said there's clearly a large consideration of attractive and repulsive terms. Okay, so that's helium-3 story. The bottom line is when gamma above, the pair interaction for the same spin is attractive, it leads to a triplet superfluidity. now, right. There are.
You can go on for 10 more minutes, so don't worry about it. Okay.
Okay. Good. Right. So there are evidence of sublattice polarized phase in multi-layer graphene. This is the experiment from the Jenny Lau's group. And so we could ask the question, can a nearly sublattice polarized, I call sublattice ferromagnet, lead to superconductivity in measured angle twisted bilayer graphene? And as you can already guess, the answer is yes. And this is shown in this phase diagram. Okay, so first thing first, this is a mapping from helium to MATBG. Up, I want you to think about AA. Up, down, I want you to think about AB. A and B are the sublattice, right? I consider valley triplets, so they are from different valley. Okay, I consider valley singlet, so they are from opposite valley. Now, if you look at this phase diagram, it's really redundant to think about, because it's really independent of gamma AB, right? Just like helium, triple pairing channel, it doesn't matter what is gamma up down. And in this case, it also doesn't matter what is gamma AB. All it matters is that there's an exponential decay of TC as you change gamma AA. And you see there's a superconductivity when gamma AA is negative enough. Now, this is, there are some details. This is linearized gap equation. So it's just eigenvalue problem. Contact interaction, spin triplet valley singlet channel, particular filling factor minus 2.4, Bistreson-McDonald model. It really doesn't matter all these details, because we don't really know what's the Fermiology very well. But the more pressing question is, which point in this vast 2D parameter space, right? Does it correspond to actually MATBG? And to answer this, because you could say that the system is really sitting right here, then there's no superconductivity. So and this is why we have to do a bit of extra work to understand different competition between what we call pseudospin paramagnon. Okay. So right. So I consider two types of interactions. This is U naught. This is similar to the Coulomb interaction that at each vertex you don't flip any of the pseudospin. So this is really just like highly symmetric possible Coulomb interaction. And then I put in a U perp that try to mimic the lattice scale effect because they would like to align spin between the two valleys in different ways. Now, with this too, I consider U perp positive. So the normal state, the high temperature state, is a spin ferromagnet. Spin is polarized, but it's a sublattice and valley paramagnet. So sublattice and valley will fluctuate. And this is the type of phase diagram that I have in mind. The type of band structure I have in mind. Okay. Now, I consider intervalley sublattice dependent potential. So I send in a Cooper pair, right, 3 and 4, from opposite valley, tau minus tau. Same spin, K, S and S. And center of mass momentum 0, K minus K. And you scatter out to different K prime. And you can write this in terms of 3 classes of diagrams. This class of diagram is what I call pseudospin density fluctuations. Basically, you can see 2 and 3, okay, the particle hole momentum that runs through the round from the same valley, same pseudospin. So it's describing density fluctuations. Whereas this diagram, the Buck-Schrieffer diagrams, you can see 4 and 2. Okay, 4 and 2 are from opposite valley. So it describes transverse valley fluctuations. If this was spin, SU2 symmetry, these two diagrams are redundant. You can relate one to the other. But these are pseudospins, and they're highly anisotropic. So their properties are extremely different. Okay, to solve this, realistically, we always have to do some approximation to the irreducible vertex function. So the one we use is just some generalized RPA. So we consider the direct scattering for both U0, U-perp, and the exchange scattering.
So just a short question, just to clarify. So pseudospin here is the valid spin, right?
Pseudo is both the sublattice and valid. Here.
Okay.
Yeah. Yeah. So so the diagrammatic analysis is really quite a bit heavy, but I will just show you the main point. Okay, the main point is if you consider the inter-valley intra-sublattice interaction, this is related to the following 4 paramagnons. So it's a symmetric plus anti-symmetric part. Symmetric in what? Symmetric in sublattice. Okay. So, and this is anti-symmetric in sublattice. Sublattice, I use sigma. Okay. So the symmetric in sublattice turns out to be the difference between these 2 paramagnon. Tau 0 is the valley symmetric. Tau z is the valley anti-symmetric. Okay. And this is because these 2 electrons are from opposite valley, tau and minus tau. And similarly for the sublattice part, for this sublattice anti-symmetric part. So in Phil Anderson's case, he has to consider the difference between 2 geometric series. I have to consider the difference between 4 geometric series because I have both sublattice and valley. Now the attractive interaction hides in this piece, AA. Okay, so AA is just given by this guy. And this guy is always attractive when U-perp is negative, and when U-perp is positive. When U-perp favors a ferromagnetic state like this, then like up and up, then this channel is always attractive. So you think then if this channel beats the AS, then you have superconductivity. So that's our pairing mechanism. In addition to this, we also know from experiment and also a lot of numerics, the filling factors where different paramagnons are enhanced, are roughly known. For example, we know that if you go to, nu equals to -3, as I show you in the beginning of the slide, you have a reset of nu equal to -3 that show you the quantum anomalous Hall effect. That thing has to be polarized in a given value, right? So at -3, then we know one of these must diverge. And it turns out that the symmetric part, this guy will diverge and lead to and kill the superconductivity. So long story short, by combining those information, we now know where we sit on this interaction space. Okay. Granted, this is reduced. This is a very simplified interaction space. Only consider AA and AB intervalley, but there are good reasons to consider so, because at first order, that's all you have. At first order, and the system will sit right here. Okay, gamma AA is equal to gamma AB. The number doesn't really matter. It just matters that they are exactly the same because they are from different value, and there's no exchange scattering. Okay, now, but we think this must be a very, very bad representation of the system. Instead, the system should be sitting right here. This is called a nearly sublattice ferromagnet. The system is trying to go through a sublattice polarized state, but not quite. They haven't go to a sublattice polarized state yet. And once you sit here, you sit here because AA now is negative and AB is positive. And then if you move around to -2 or -3, you move the system away from this point in this direction to increase. This direction is parallel to this line. Okay, so this line is the line where the sum of the two, the difference of the two is 0. Okay, so you move in this line because you move in a direction that increase AS, the symmetric channel, and decrease the anti-symmetric channel. And if you know sublattice polarized system, there's no reason why gamma AA is still attractive, right? You will come back to this region and you don't have superconductivity. Okay, so let me, right, 4 minutes, good. So let me just summarize. I hope this phase diagram paints a convincing picture of the superconductivity dome that we draw here. Okay, so we have a superconductivity dome. The glue is mediated by sublattice paramagnon. As you approach -3, although the density of state is still increasing, the fact that you are approaching valley polarization kills the superconductivity. And valley XY instability might also kill superconductivity, but it might also just vary with simply the fact that density of states is small here, right? Because this is coming out from reset. Okay, right, okay, good. Let me just end the talk 3 minutes earlier. All right, I'll now start to take questions if there are any.
Yeah, okay, so thanks. Yeah, so I mean, please unmute yourselves and ask questions if you have any. It's Q&A time. All right.
So maybe I can add something. So, okay, so in the very last part, no, of your talk, so we have fluctuations of this pseudospin, which is a mixture of sublattice and valley, right? Mm-hmm. So I don't know if I get the message. So valley polarization basically destroys superconductivity, but somehow sublattice. So what is and sublattice polarization has the same role, or?
Yeah. So yeah, it's important to twist all these things first try. So let me try to give a sort of physical hand waving picture. So we consider a valley singlet state, right? The pairing, the superconducting state. Okay, before that, let me just make one analogy. I think this will help. We know that in the BCS state, let's say spin singlet, right? BCS state, you can calculate the spin susceptibility. And we know the spin susceptibility drops exponentially as a function of temperature, right? Goes as the Yoshida function, right? And at 0 temperature, the spin susceptibility is 0. This means the superconducting, the singlet superconduct, the singlet BCS singlet screen greatly reduce the spin susceptibility. It means they don't like to be spin polarized, which makes sense because they are singlet. The same thing happens here. This is a singlet superconductor, and when you approach her, the system is trying to polarize in Ising direction. So they just want to go to an ordered state where tau z is not 0. So they don't like this, and this kills the superconductivity.
Because the role of valley is clear to me. It's precisely this analogy. It's more about what happens with sublattice, because I don't have a picture of which is the structure of the pairing order in sublattice space, for example. So what is the role of the sublattice here? So I'm confused with the role of the sublattice.
So the sublattice is because we think the system is almost a sublattice Ferro. The system is on the border of sublattice polarized state. And that's because if I can show you my cartoon band structure, this is sublattice basically want to scatter you from ask about the susceptibility. from mixing the conduction to valence band. Because sigma z, as you know, flips, the pseudospin from Singapore to Greenwich, right? Right, and in graphene, they just want to go conduction to valence. They want to mix them, and they can always be mixed. They can always be mixed over a wide range of energy scale, and therefore they are always trying to be sublattice polarized. Is that what you are asking? Where is the glue?
So I guess my question is simply the fact that the samples are aligned with the boron nitride. So is this explaining why, if you align the sample with a boron nitride, that tends to suppress superconductivity?
Yes, that's how we build our theory. If you suppress, then there's no sublattice susceptibility enhancement.
It's that right? Okay. You are just killing the sublattice. So you are killing fluctuations in sublattice degree of freedom, and that's it.
Yeah,
so that's it. So I think, So I understand.
If you find any samples that have superconductivity in a sublattice polarized state, let me know. I have to change. Okay.
Are there any questions, or can I follow up on that? So I want to understand a little bit better that issue. So the point is that, so to put it in terms of energy scales, what you're saying is that essentially there is a large energy scale which is giving you at nu equals -3 the valley polarized state, which is a ferromagnet, right? And then there is a smaller energy scale which would like to break this sublattice symmetry, but doesn't. I mean, is that the right way of thinking about it, or? I mean,
could you repeat? Yeah.
Maybe you can put the phase diagram again, or
the phase diagram.
I mean, the conclusion where you had this kind of like schematic phase diagram. Not this one. The next one, I think. Yeah. So at nu equals -3, you have a valley Ising kind of. I mean, the anomalous Hall. I mean, the quantum anomalous Hall insulator, right?
Sometimes, not all the times. Depends on the sample. But we know for sure that at some point you could go low enough in the whole density, then I think the state will always want to be polarized in a given value. But whether they will lead to sometimes they don't lead to anomalous Hall effect because the C2 is not broken. I mean, the Dirac point is not opening yet.
Oh, but even if you don't have a gap at the Dirac point, you have a metal which has a Chern number, right? I mean, in the band, you have a Chern number. I mean, a non-zero Chern number. So that should have an anomalous bulk anomalous Hall effect, not a quantum anomalous Hall effect in the sense that you have conduction along the edges, right?
But that's not. For example, you look at Yeffatov's data, that's not there.
But it should be there, right? Is if you move the chemical potential away from unless there is some kind of reconstruction of the bond structure due to the fact that you're changing the density, right? I mean, you just think of like having in your initial picture, right? What you were explaining to Ilya, right? That you have this Chern insulator, and then I just stop this Chern insulator. I have a metal, right? And this metal should have a finite sigma xy, right? So it's like if you take the Haldane model and you just stop it, right? Oh,
so Miguel, can I interrupt for just a second? So I got the time zone wrong, so I'm joining this late. In order to maybe there are two important points, and maybe Chunli already made them, but in order to suppress superconductivity, you don't actually have to have valley polarization. You only need to be closer to satisfying, closer to a valley polarization instability. And so I think that, the balance of the, typical experiments don't see a anomalous Hall effect at -3, for example, or -2.8. But there's good reason to believe that they're close to that instability, which occurs on the other side, differs by the.
Right. This might be helpful. Yeah. Yeah, the
Right.
Venn diagrams. Yeah.
And another point that Chunli may have made is that the susceptibility for valley polarization is, has a big part proportional to the density of states, which we know increases as you go from -2 to -3. But the sublattice susceptibility, because it's really an interband response, doesn't have that instability. Or doesn't have that tendency to grow with the increasing density of states at the Fermi level. So that might be relevant.
Thanks. Any further questions? Okay. Well, so the peculiarity of this seminar series, I haven't said this at the beginning, but I said that in the previous seminar. So if you attended, is that now we are going to have a 5-minute break. So we are going to stay open. I mean, this meeting will not end. And after 5 minutes, we come back with a cup of coffee or tea, or with a cup of water if you don't want to put any caffeine in your system. And we can talk more or less informally. This is not going to be recorded with Chunli. So we are going to finish the recording here. And after that, after this break of 5 minutes, you grab a coffee and we are back. Okay. So see you in 5 minutes.
Okay.